752 is the same example, but we're looking at the second part. You're going to look at 400 degrees C, 10 bar, that's 10 bar. You're going to find the volume, specific internal energy, specific enthalpy, and the dew point. Your reference state is liquid water at triple point. The liquid water at triple point. This is your triple point. Liquid water at triple point. Okay. So I'm going to show you guys the. Sorry, I need to close this first. That's the steam table. Can you see the steam table, guys?
Yes, doctor.
Okay.
Yes, doctor.
Okay, you're looking at 400. 400. That's 400. 400. And the pressure is 10 bar. Okay, so now I'm going to need to scribble. The problem with this thing is sometimes I can start noting. Okay, that's 400. That's 10 bar. Okay. What is the volume? That's the volume. That's the volume. Okay, that's volume. What is the internal energy? That's the internal energy. What is the enthalpy? That's the enthalpy. And what the unit? You have to look the unit up inside your steam table. Because the unit here, I don't have the unit here. But the unit, you look at the steam table, B7, table B7. If you look that up, let me look inside my textbook. B7, table B7, you should have the unit written at the bottom of that page. Okay, the unit for your internal energy is kilojoules per kilogram. The enthalpy is also kilojoules per kilogram. The specific volume is meter cubic per kilogram, which is written inside here actually, which is written here. That's kilojoules per kilogram, that's meter cubic kilogram. And the dew point is that value. That's the dew point when it is saturated vapor. That's the dew point. So everything is there. You don't even need to calculate anything. Any questions? Any questions? No. Good. That's the example 752 for the second part. That's done. So let's continue with more. Am I speaking to myself? Yes. Oh dear, this is getting terrible.
We can hear now, doctor.
Oh, just now you can hear me, okay? Okay, somehow my internet, the cable just somehow, when I'm. Okay. Anybody, do you have? Guys, can you hear me now?
Yes, doctor.
Clear now.
Yes.
Oh dear. Anybody?
Yes, doctor.
Yes, doctor.
Yes.
Ibrahim? Anybody?
You're breaking down, like you're not clear.
Not clear.
From moment to moment, your voice breaking down.
Can you hear me now?
Yes, I do.
Okay, let's look at this example then. This is interpolation. I hope you guys have come across this before. Have you guys come across interpolation before?
Yeah.
Yes.
Yes.
It is nothing new, isn't it?
It's not.
Okay. So how to calculate x? Show me the calculation. Give me a value. I just give you guys some time to do it, and I'll ask for the answer later on. For those who doesn't have your calculator, you need to calculate it actually. You really need to calculate it. Calculate it for me. I'll give you guys some time to do it. I don't have the answer, so whatever answer you get, if most of you get the same answer, then that's the correct answer. Get the value of x using this equation for interpolation, or if you don't want to use that equation, you can easily use your calculator. You don't even have to use that calculation equation.
X equal 6.5.
6.5. Everybody got the same value? The rest of you guys? Everybody got the same value?
Yes, Doctor, 6.5.
Okay,
Yes, doctor.
good. So you know how to interpolate. I'm not going to show the calculation, okay? Unless somebody say how to do it, I haven't come across it before. Anybody? Everybody get the same answer, 6.5. Okay, nobody responding. So that means I'm assuming that everybody get the same answer, 6.5. If you get a different value, please, recalculate. Or if you really don't know how to do interpolation, tell me. We will show the example. But the example is there. Okay, let's go and proceed to the next. Let's look at the next slide. Okay, this is saturated steam table. This is from appendix B5 from your textbook. We have looked at this actually just now when we are doing example 752. So this is the steam table. Let's okay. The reference state is the triple point. I did mention that. This is again a continuation of the steam table. Okay, need to point out this to you guys. When the steam tables are available, if you need to calculate the steam, the value of the enthalpy for steam or whatever value you need, for example, the specific volume, do not have a look at the bottom. Or no, you have a look at this. Do not use the ideal gas law because the steam table, the data is already done for you. So you don't need to use this ideal gas law. When you use the ideal gas law, that means you are just getting an approximation. But when you look at the steam table, the value is very accurate. So do not use, when you have the steam table, do not use the ideal gas law. Okay, this is superheated steam. Now have a look at the table for superheated steam. If I can get there's a line here. Okay, there's a line there. Anything below that line is liquid. Anything above that line is vapor. Okay? So for example, over here you have a pressure of 0.5. The saturated, let me undo that. Can I undo that? Yes, I can undo it. At that pressure, that is the temperature. So if you have a temperature of 50, for example, obviously you will have liquid here. But if you have a temperature of 100, which is above 81.3, that means at that condition, it is vapor. So that's easy enough to know. Anything above that line is vapor. Anything below that line is liquid. Okay, guys? That's your superheated steam. Okay, let's proceed. That is another example of a superheated steam table. This table is slightly different from your textbook because this is from a thermodynamic textbook by Changel. This is another way of looking at the steam table. You have the pressure, you have the temperature. So let me scribble something. Okay, here you have the pressure. That's the pressure. Oh, why I'm not getting anything? That's the temperature. That's the pressure. Yeah. So you have different pressure, different temperature. This one is temperature. The saturated temperature. This is saturated temperature. Yeah. That is the dew point. That's the dew point. Can you guys hear me? Guys,
Yes.
good. Okay, that's how, another example of a superheated steam table. That's another one, the continuation of it. So forget about this. Let's see whether we're going to. Okay, let's look at this example. You're going to look at superheated steam. You're going to look at superheated steam that enter the turbine at 1.4 megapascal. That's 1.4 megapascal at a temperature of 350 with a velocity of 80 and the height of 10 meter. Oh, everything is here. You have the potential energy. You have the kinetic energy. Yeah, that's the inlet, and you have the outlet. This is the outlet. Yeah, that's the outlet. Okay, now the heat loss from the turbine. There's a heat loss is 10 kilowatts. Your amount coming in is 1 kilogram per second. Is coming out as saturated. This is saturated steam. That's why the temperature is not given, just the pressure. You need to find out the power. Guys, how to do this? What system?
Using the
It's an open system, so I think we need to use the open system equation.
Good, it's an open system. So you need to have the open system equation. Okay, let's use my example. Let's look at this example. This is okay. Now you have internal energy. You have the velocity. You need to calculate the kinetic energy. You have the height. You need to calculate the potential energy. So I'm going to unshare the PowerPoint and share you guys the iPad. Okay, it will take some time. Okay. Oh dear. Okay, the equation. You need to write the basis first. What is the basis, guys?
1 kilogram
1
per second.
kg per second.
1 kilogram per second. 1 kilogram per second. I'm having difficulty with this pen because my previous pen doesn't work. Let me get this properly. 1 kilogram per second of inlet steam or feed. Right, you need to write down the feed. Yeah. 1 kilogram per second of what? Of superheated steam. Superheated steam. Write it down. Superheated steam. You got to write everything down. Okay. Now, where is that's the inlet? We're going to give it a symbol of 1. That's the outlet. We're going to give it a symbol of 2. Okay. So our equation, do we have a basis? We have a basis already written. We need a reference state. We will decide what reference state to use once we decide where we're going to get our data from. Okay, so now we're going to write the equation. The system is an open system, so it's delta H plus your energy, kinetic energy. Oh dear, why am I not getting? Okay, potential energy, kinetic energy is equals to Q dot plus shaft work. Okay. So now, where are we going to get our data from? I mean, our enthalpy from?
on the table.
Steam table.
Steam table, superheated steam table. So if you're going to use the steam table, your reference state must be the same as that of the steam table. So what, guys, is the reference state of the steam table?
Superheated.
Sorry? Anybody?
Repeat.
What? Sorry?
Just a minute.
It should be at triple point, isn't it?
Yes.
Okay, triple point for liquid water. Liquid water. Liquid water. What is the triple point? That means the temperature is 0.01, the pressure is 0.00611. Remember just now when we were looking at the steam table? So that is your reference state. Okay, now enthalpy Mars, what do we have? Let's look at what we have. We have, this is Q. This is Q. It is lost. Let me undo that so that I need more space. Q is equals to what is the symbol, please? Positive or negative?
Negative.
Negative because it's coming out. Yeah, that's negative. Okay, let's look at our steam table. I'm going to need 1.4. I'm going to write over here my enthalpy, specific enthalpy for number, this is denoted as 1. Yeah? This is H2. Going to get it from there. Yeah? So this is 1. This is 1. So let's tidy up a bit. This is H enthalpy 1. Yeah. We're going to look at the steam table. So I'm going to unshare this. I'm going to show you guys the steam table, superheated steam table. Where is my PowerPoint? Okay. Okay, this is our steam table. Okay, let's look at the example. The inlet is coming in at 1.4. Where is 1.4? 1.4 is the other table. Okay, 1.4. Where is 1.4? Have a look at my cursor, please. Where is 1.4? That's 1.4. Okay, I'm going to scribble. That's 1.4. Oh dear, why I'm not getting, that's 1.4. Why I'm not getting, oh God, this is terrible. That's 1.4. Okay, what temperature is the steam coming in at? 350. Where is 350? That's 350. Okay, so 350. So what is the enthalpy? If you draw a straight line along here, where is the enthalpy? That is
Three.
enthalpy.
3-1.
Yeah, 3150. 3150.1. The unit is
Kilojoules per kg.
kilojoules per kg. Okay. Well, what about this? The outlet? The outlet, the pressure is 0.5. So we're going to look at the next, the one before that. That is 0.5. So have a look at 0.5. Can you find 0.5? That's it here at the bottom here. My cursor is pointing at it, and the temperature is not given, but it is stated that it is saturated. So which one are you going to look at? That's saturated, isn't it? That is saturated. So your enthalpy is that value. Where's your enthalpy? That value. That value, 2748. Please look at my cursor. That is the pressure. Oops. That is the pressure. And this is saturated superheated, saturated steam. And that is the enthalpy. So I'm going to write that down. My enthalpy is 2748.1. Hold on, I'm going to write this. 2748.1 kilojoules per kilogram. That is my enthalpy, H2. So now I'm going to go back to my, unshare this and go back to my iPad. This is quite difficult, really, teaching calculation online. Okay. Okay, guys, I already wrote down the value. So I'm going to show you guys the value. Just now 3150.1. I'm going to erase that. 3150.1. The unit is kilojoules per kilogram. Yeah. So we have our enthalpy 1 and enthalpy 2. So from that values, we should be able to get delta H, the specific value. but we don't want the specific value. What do we want?
The change.
The change. Okay, so we're not going to use the cap, we're going to use the dot. Okay, for the dot, if you remember, the dot has a unit of time. So it should be kilojoules per second. So what you have over here, when you get the value from the steam table, it is kilojoules per kilogram. So obviously you need to get rid of the kilogram. So in order to get rid of the kilogram, it should be multiplied with the mass, which is kilogram per second. Okay? Multiply with the specific enthalpy, which is kilojoules per kilogram. So when you do that, you cancel off the kilogram, you end up with kilojoules per second. So now, when we want to do our calculation, oops, I want to shift it further up, but I'm not doing very well. Let's do that first. Oh dear. Hold on. It should be delta H is equal to summation outlet or final M flow rate specific enthalpy minus summation inlet M flow rate specific enthalpy. So that's your equation when you want to do the calculation for the rate of enthalpy change. Okay, now let's go to the next page. Yeah. What do we have? We have this equation. Out. If you want to write full, it will be that equation minus summation in rate enthalpy change. Okay, now what is the mass just now? Anybody?
1
kilogram.
Okay, so it's the same. Inlet and outlet is the same, so you can take it out. M out. So your out value just now we denoted is as 2 minus your enthalpy. Oh dear, let me undo that. Because it's too close. It's too close to the. I need to undo that. Okay, let's rewrite that. Going to be mass. Yeah. H specific out minus in. We get rid the symbol of 2 and 1 just now. So your mass is 1 kilogram. 1 kilogram per second. Your enthalpy just now. Let's go back to the value. The enthalpy just now, the out value is 2748. That is the value. 2748.1. I'm going to write that. 2748.1 minus, let's go back to our previous slide. Your initial enthalpy, inlet enthalpy is 3150.1. 3150.1. 3150.1. So that the unit is kilojoules per kilogram. So cancel your kilogram. So what is your answer? Anybody?
Minus 402.
Minus 402. So that's in kilojoules per kilogram. Sorry, second. Second, not kilogram. So that is delta H. Only one part of it is done. Let me erase that. Get it proper per second. Okay, that's the first part. Now you have your kinetic energy. Kinetic energy, you have the dot there. It must be half mass and use different of u. It's a different of u. Let me undo that. U2 square minus U1 square. Okay, let's look at our diagram. Your velocity U is there. That's the U. That's the velocity. So U, write down. That's U2. Subscript U1. That's subscript U1. U1 is 80. U2 is 50. So somebody take note. U2 is 50. U1 is 80. So let's go back to the calculation. So half. Your mass is 1 kilogram per second. Okay, now your U out. What's the value just now?
50.
Okay, 50 squared minus 80 squared. What's the unit? Meter square per second square. Oh dear. Why I'm not getting, I cannot write the second square. Okay. Remember how we changed the unit? You guys, we did that example previously. Yes. So do the calculation. Now let's first get the value first. Then we change the unit. Multiply it. 50 square minus 80 square divided by 2. Get the value first. Then we change the unit. What's the answer?
Minus 1950.
Minus, again, repeat 9, 1950.
1950, yes.
1950. Okay, that the unit is kilogram second meter square second square. Okay, now we need to look at the conversion table from the front, from the from the back of, from the front of the textbook. What do we need? We need it to be having a unit of kilojoules per second, at least kilojoules per second, because this is the unit that you have for your change in enthalpy. If you change that into watt, it become, let's see, change that into watt, minus 402, it is kilowatt, isn't it? Kilojoules per second is kilowatt. So now, let's get this into the unit into joules first. 1 joules.
I think 1 kilojoules equal 1,000 meters square second square.
Okay, 1 kilojoules. You're going to use kilojoules directly. 1 kilojoules, 1,000. What?
Meter square second square.
Meter square. Meter square?
Second square.
Kilogram. Sorry? 1 kilojoules is equals to?
Let me just check again.
Because I know 1 kilojoules is equals to 1 10 power 3.
Meter square second square.
Okay, hold on. Let's look at the textbook. The 1 kilojoules is 1 Newton. 1 kilonewton. Okay, let's do it step by step, because it's not. Okay, 1 joules equals to 1 Newton meter. Okay, we do it step by step. And 1 Newton meter is equals to 1 kilogram meter second square. I'm using the slide from the unit from the first slide. And let's see whether we need to cancel meter square, meter square, meter square. Cancel that. Second square, second square, second square. Newton, Newton. Okay, kilogram, kilogram. So we end up with joules per second. Okay, now 10 to the power of 3 joules per second is equal to 1 kilowatt, isn't it? Is that right?
Yes.
Okay, cancel the joules, cancel the second, we end up with kilojoules. So what's the final answer? Is going to be the same, or is it going to be different? It's going to be negative 1.95 kilojoules, isn't it? So you divide by 10 power 3. Is that correct, guys?
Yes, doctor.
Okay, that's your kinetic energy. How about potential energy? Potential energy, I'm going to use the next page. Potential energy. Okay, potential energy is equals to m dot gravitational acceleration and the difference in the height 2z1. Okay, so your mass again is 1 kilogram per second. Your gravitational acceleration 981 meter second square. And the difference in the height, let's go back to our diagram. Yeah. The height is coming in at 10 meter, coming out 5 meter. Yeah, this is the height 10 meter, that's the 5 meter. So out 5 in 10. Out 5 in 10. Is that correct?
Yes,
Yes,
doctor.
yes.
Meter. Okay, now again, get the answer please, then we change the unit. It's almost 10 to 10. You got to hurry up. I'm going to write down the unit.
Negative 49.
Negative?
49.
Negative 49.
Okay. Oops. 49, I'm in a hurry, but I'm messing it up. A kilogram, second, meter, second square, and there's another meter. Now, we did the same conversion again. Let me see the first slide. 1 joule is 1 Newton meter. Yeah, 1 Newton is equals to kilogram per meter second square. And now let's see, cancel, kilogram, our meter, cancel, meter, second square. So we end up with 1 joules per second. So 10 to the power of 3 joules per second is 1 kilowatt. So you cancel off the joules, cancel off the second, you get the same negative what? Negative 49
0.
times 10 negative 3. I just write it like that, okay? So now everything is there. Put in inside your equation the final value that you have. Let me erase that. Yeah. You have delta E kinetic, your delta potential equals to your Q. Your Q, you get it from the equation itself, plus WS. That's your solve for your WS. Put everything inside there. Remember, when we were looking at the problem, I need to hurry up. Okay, we have this is your Q minus 10 kilowatt. Okay, your delta H is that value. Okay, your kinetic energy, that value. Okay, next, your potential energy is that value. So substitute everything inside here. Solve for the turbine, the power of the turbine. What kilowatt will you get?
Negative 414.
Negative
414.
414. Let's see what is the answer that I have on my slide. Okay, where is my slide? Hold on, let's unshare this. Look at our PowerPoint. Let's look at our PowerPoint. Okay, where is my PowerPoint? Okay, let's see where is the. Okay. Oh, slightly different. Most probably the difference is due to the round of error because we are using a different steam table. Any comment on the problem? It's slightly different, the answer. This is negative. Why is there a negative 414 and the answer is positive?
The convention of sign.
Okay. Should it be negative, guys?
It depends on how do you say it.
Okay, yeah, but common sense. Now that we are using for the negative to be the outlet, that mean that the power should be out. Remember, look at the question itself. Determine the power turbine power output.
Yes.
Yeah.
Yeah, output supposed to be negative.
Yes.
Yeah, so we should be getting negative. Okay, the only difference is that the answer is not close to the. It's quite close. It's just not. It's not exactly the same, but I think that's due to the run of errors and in the calculation. And another thing is because maybe that the author is using a different steam table. Maybe run a bit error there. Just round off calculation error. Okay, guys. Any problem with this example? It's almost time up. Any problem? Is it clear?
Yeah, yes, clear, doctor.
Okay, good. That's it for today. It's already 9:53. So have a look at this example. This example is not actually from the textbook. The example that I just showed you guys is not from the textbook, but it's a good example whereby you have everything there. Everything is there. You have the kinetic energy, you have the potential energy, you have the work, you have the you have the heat, and you use the steam table. How to use the steam table? Yeah, guys. Anything you guys want to add or anything you want to comment?
Doctor,
Yes.
I just got it minus 393.99.
Oh, that's very close. Oh dear, that's that.
No, because I think for if it shows 414, then the value for Q it won't be changed. If you take it from to the other side, it will be positive instead of negative.
I'm not
It's
talking about
cubeless.
positive or negative. I'm talking about the value because the symbol we have to be negative. It has to be negative.
Yes, it has to be negative if it was with WS, but if you take it to the other side, it will be positive with respect to WS.
Oh, you
Works.
did the calculation wrongly. We did not move the Q to the other side.
That's what I mean.
Okay.
If the Q is negative, it will be positive.
Okay, redo for the rest of you guys. Solve for the work. Not do so. Bring over the Q to the everything to the right hand side. Q is going to be on the left hand side. Okay. See whether you're going to get the same answer as. But it has to be negative, obviously. But is it 39 something? It's not 414.
393.
Yeah.
Yes, doctor, it's
19.
394.
Okay, so that means we got it almost. We exactly got it, the answer. We got the answer exactly. It's not 414. Okay, please, whoever got 414, double check your calculation. Remember, the Q should be on the other side of the equation. Okay, guys. Yeah, guys.
All right, that's it.
Okay, so see you guys tomorrow afternoon at 2 p.m. Same link. We will continue with more examples. Okay, guys. Yeah, thank you very much for having you guys very early in the morning. As always, we will always start at 8:15. The reason is because I don't want to rush. I don't want to be in the situation whereby I will start to panic if I don't be on time. Yeah, I arrive here 5 to 8, but I want to settle down. I want to set everything up so that everything is, I'm I'm not in a hurry. So we will always start at 8:15 in the morning, and we will start at 2 p.m. in the afternoon. Okay, guys? Okay, guys, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Thank you, Rod.
Welcome.
Doctor.